All right. So this last topic deals with the what the chapter calls the colligative properties of solution. Colligative properties are properties that depend on the amount of matter present. So the more solute that I have in solution, uh, the greater the effect on this colligative property. And the two colligative properties that we are looking at in these topics are freezing point and boiling point. And that should be a T, not a D. And what you'll notice is freezing point as a colligative property, as I add more solute, becomes depressed. And boiling point becomes elevated. So maybe it makes sense why we use ethylene glycol, we use antifreeze to lower, to depress the freezing point of the water in our radiator, the solution in our radiator. And it also has a reverse effect. In the summer, it elevates the boiling point to make it boil at a higher temperature than it normally would. So how do we find the freezing point depression and the boiling point elevation? That's done with two very, very easy to use formulas. The freezing point depression is going to be equal to this thing called the molal freezing point depression constant times the molality of the solution. Now, I do want to point out that what we are solving for here, when I multiply the molal freezing point constant, which is given, this is given, and here it is right here in the problem. When I multiply that times the molality, what I get is this delta TF. That delta symbol means change in. So this delta sign means change in. This is the temperature, and that sub F means the freezing point. That's what it's insinuating. So what we're literally finding is the change in the freezing point of this solution. Now think about what I just said about colligative properties. These two colligative properties. Freezing point is depressed, boiling point is elevated. So what we are finding is the change in the freezing point or the freezing point depression. This is going to tell us how much or how many degrees Celsius the freezing point is going to go down with a solution of this molality. Okay? So the freezing point depression is equal to the molal freezing point depression constant, which is 3.36, and the units I'm using here, degrees Celsius times molality, and then we're multiplying it by our molality, which we have to find, but we know how to find molality. It's moles of solute per kilogram of solvent. Well, what is our solute? Urea. We have 32.47 grams. So 32.47 grams of urea. Urea has a molar mass of 60.06 grams. 32.47 grams divided by 60.06 gives me 0.5406 moles. So we have that many moles of solute or urea, and we divide that by kilograms of solvent. That many grams of urea is dissolved in 950 grams of our solvent X. It needs to be in kilograms, so that's 0.950 kilograms. So the molality is 0.5 molal. So I'm going to take that and plug it in over here. Times 0.569. And I'm going to carry a few more digits here. Our units of molality go away. And the freezing point depression is that times 3.36, 1.912, rounded to significant digits, 1.9 degrees Celsius. That is our unit left. Okay, but that's not our answer. That's the freezing point depression, but it's not our final answer. We need to figure out what the new freezing point is. What's the original freezing point? There it is. Negative 7.9 degrees Celsius. So it's going to depress that even more. So negative 7.9 minus 1.9 is going to give us a new freezing point. New freezing point of negative 9.8 degrees Celsius. Here's our original freezing point. Substance X has a normal freezing point of that, but we add solute to it, and because of the colligative properties of solutions, as I add solute, the freezing point now is going to be depressed. I don't have pure X anymore. I've got substance X with something dissolved in it. The new freezing point is this, with this much solute, with this concentration of solute. Now, if I add more solute, it's going to go down more. If I add more solute, it's going to go down more and more